Every single time you fill up your car, board a flight, or walk on a freshly paved road, you are using something that started out as a thick, smelly, almost useless liquid pulled from deep underground. It looks unimpressive. It is dark, it is dense, and it has no obvious purpose sitting in its raw state. And yet, this one substance quietly powers nearly every form of transportation on Earth, heats millions of homes, and forms the raw material for plastics, medicines, and synthetic fabrics. Right now, the world extracts around 94 million barrels of crude oil every single day. That is enough to fill over 150 Olympic swimming pools daily. And yet, in its raw form, you cannot put it in a car, you cannot fly a plane with it, and you definitely cannot pave a road with it. So how does this dark, sticky mess become jet fuel, gasoline, plastic, and asphalt? Today, we are breaking down exactly how crude oil refining works, from its surprising origins in the 1800s to the massive industrial science running behind the walls of modern refineries. Here is something most people do not know. Oil refining was not invented to power cars. It was invented to power lamps. Back in 1859, Edwin Drake drilled the first successful commercial oil well in Titusville, Pennsylvania. At the time, people were not thinking about gasoline. That word barely existed yet. What they wanted was kerosene, a cleaner and cheaper fuel for lighting homes at night. Whale oil, which had been the dominant lamp fuel for generations, was becoming expensive and difficult to source. Crude oil offered a solution. The early refining process was remarkably simple. Heat crude oil in a basic metal still, let the kerosene evaporate, collect it in a separate container, and discard the rest. Most of the oil was considered waste, a messy byproduct that nobody wanted. Then everything changed. In 1908, Henry Ford introduced the Model T, the first automobile built for ordinary working people. Within a few years, cars were everywhere. Suddenly, millions of people needed gasoline, and refineries that had been built to produce kerosene were nowhere near ready for that shift. The pressure to produce more fuel, more efficiently, drove an explosion of refining technology and engineering innovation across the entire industry. What started as a simple distillation process quickly evolved into one of the most complex and precisely engineered industrial systems ever built by human hands. Today, the United States alone operates 132 refineries with a combined capacity of over 18 million barrels per day, and global refinery capacity exceeds 100 million barrels per day. All of it traces back to that first well in Pennsylvania and the simple human need to keep the lights on. Before you can understand how refining works, you need to understand what crude oil actually is, because it is not a single substance. Crude oil is a mixture of hundreds of different hydrocarbon molecules, chains of hydrogen and carbon atoms bonded together in varying lengths. Some of these chains are short and light, and they evaporate easily. Others are long and heavy, and they behave more like wax or thick syrup. This difference in molecular size is critical, because the lighter the molecule, the more valuable the fuel it produces. Light crude oils yield gasoline and jet fuel more easily, while heavier crude oils require significant additional processing before they become useful. Crude is also classified by its density, measured by what is called API gravity, and by its sulfur content. Low-sulfur crude oil is called sweet crude. High-sulfur crude is called sour. Sweet crude is easier, faster, and cheaper to refine, which is why it consistently commands a higher price on global energy markets. The first major step in turning crude oil into something useful is separation, achieved through a process called fractional distillation. Inside a refinery, crude oil is pumped into a furnace and heated to around 350 to 400 degrees Celsius until most of it vaporizes. That hot vapor is then pushed into a distillation column, a towering steel structure that can stand over 30 meters tall. Inside the column, a remarkable thing happens through nothing more than basic physics. Because different hydrocarbon molecules have different boiling points, they naturally separate as the vapor rises and cools. Light molecules travel higher before they condense into liquid form. Heavier molecules condense lower down. Each level of the column collects a different fraction of the crude. From top to bottom, the column separates out refinery gases like propane and butane, then gasoline, then naphtha, then kerosene and jet fuel, then diesel, then heavy gas oil, and finally a thick dark residue at the very bottom. Here is a fact that captures just how efficient modern distillation has become. U.S. refineries produce an average of 45 gallons of finished products from every 42-gallon barrel of crude they process. That extra volume comes from what the industry calls processing gain. Refined products are simply less dense than the raw crude they came from. But distillation only separates what already exists in the crude. And the problem is that crude oil naturally contains far more heavy molecules than the modern world needs. Gasoline and jet fuel are in constant high demand, while heavy fuel oils are far less valuable. So refiners take a critical extra step. They break the heavy molecules apart in a process called cracking. Using carefully controlled combinations of heat, pressure, and chemical catalysts, large hydrocarbon chains are split into smaller, lighter, more valuable ones. One of the most widely used methods is fluid catalytic cracking, where heavy gas oil is mixed with a fine, superheated catalyst powder that triggers chemical reactions, splitting long chains into shorter ones, dramatically increasing the yield of gasoline and lighter fuels. Another method, hydrocracking, injects hydrogen under high pressure, which not only breaks molecules apart, but simultaneously strips out sulfur and other impurities in the same step. Without cracking, global refineries could not produce anywhere near enough gasoline or jet fuel to meet world demand. The entire modern transportation system depends entirely on it. Not all refining processes involve breaking molecules. Some involve rearranging them entirely. Catalytic reforming takes low-value naphtha, a fraction that comes out of distillation but has limited direct use, and restructures its molecular shapes using heat, pressure, and a catalyst. Straight-chain hydrocarbon molecules are converted into ring-shaped or branch structures that burn far more smoothly and efficiently inside an engine. This directly increases a fuel's octane rating, which measures its resistance to premature ignition or knocking inside cylinders. High-octane fuel allows modern engines to run at full performance without damage. As a useful byproduct, catalytic reforming also releases hydrogen, which is then used in the cleaning stages downstream. Because crude oil contains sulfur, and burning sulfur produces sulfur dioxide, a serious air pollutant and a major driver of acid rain, every fuel must pass through a cleaning stage called hydrotreating before it leaves the refinery. In this step, hydrogen chemically bonds with sulfur compounds and removes them from the fuel stream. Today's environmental regulations are extremely demanding, with many countries requiring diesel fuel with sulfur levels no higher than 10 to 15 parts per million, and refineries are precisely engineered to meet those strict standards.